All right, welcome everyone. I am JJ. Let's tackle an example problem. So we're just saying let's draw our shear moment diagrams for a compound beam here. We are fixed at A, internally pinned at B, roller support at C. If we think through our overall free body diagram, I'd have AX, AY, MA, CY. Four unknowns. I can't find that with statics. Even though AX isn't going to matter for our problem, still takes one of our equilibrium equations. We can't find everything out here. If I break this into pieces, though, treat it like a frame, explode it into individual pieces, I can make a free body diagram of each one. That first section, AB, we still have MA, AY, BY, technically AX in there, but it's 0. But four unknowns, three equations, I can't find everything. On BC, though, I'd have BY, CY, CX, or BX. BX is going to be 0, leaving us with two unknowns, but only two equilibrium equations left, because that sum of the forces in the X would get us BX to 0. But I can find what's going on here. We're actually going to start there so I can find my support reactions and make a free body or make a shear moment diagram. So let's come in and we're going to work with BC first. So working with BC. I have BY and CY as unknowns. So let's sum moments about point B with positive, going counterclockwise, summing my moments about point B. Is going to get me. I have 25 CY, 25 CY, minus my distributed load, minus area. My height is 10. My base in this would be 25 plus 10, 35. Gets me the area. Times the distance from B to the centroid of my distributed load will be halfway into it. So times 35 over 2 gets us to 0. Looks like I ran behind a picture there. Equals 0. I can solve that for CY. CY is going to work out to be equal to 245 kips going straight up. From there, with that one known, I can sum forces in the Y and I'll get BY. Summing my forces in the Y direction. I have CY going up 245. On this free body diagram, I'll put BY goes up, so plus BY minus my distributed load, or minus 35 times 10. Minus 35 times 10 equals 0. Which if I solve for BY, I will get BY is 105 kips. 105 kips. That's an internal connection. So let's get our direction. We are going up here on, we're working with BC. On BC. And that matters for us because when we work with AB, this will be equal and opposite. We could also say BY is the same magnitude, 105 kips. That's our equal. Opposite, though, means it's going straight down. On our next member, on AB. And I again ran into a picture here. On BC. On, we'll just scoot it over. But we can work with those and then move on to my other free body diagram. BY, we'll just write small. BY was 105 kips going up on BC, and it worked that time. BY is 105 kips going down, equal and opposite, on AB. If I know BY, I can then move to AB, and I can work with this free body diagram and find everything out then. So working with AB, we would say, well, I can sum forces in the Y and get AY. Summing my forces in the Y direction. I have AY. I'll need to subtract out my distributed load. 15 times 10. It's area, base times height. And I'll need to subtract out BY because we're working with the AB piece going down. Minus 105 gets us to 0. Or AY is 225 kips. And it is going up. We have one last support reaction, the one everyone tends to forget. We need to get that moment. So we can do that by summing moments anywhere we want. With positive, going counterclockwise. Let's sum up our moments about point A. This is going to get us, well, I have a variable here, MA. So MA, my BY will cause a clockwise rotation. So minus BY 105 force times my distance is 15. Minus my moment from the distributed load. Minus area, base 15 times height 10 times my distance from A to the centroid would be halfway in, which since it starts at the same point, it's just 15 over 2. Gets us to 0. Or my moment here, MA, is 2,700 kip feet, and that is going counterclockwise in the direction we assumed there. That gets us enough. I can come in and start dealing with shear moment stuff. We have our support reactions. When we deal with the shear moment diagrams, really we want to use just the overall free body diagram. Those internal connections here only matter for us. There's useful info we can find from that, but they only really show up in the shear moment diagram to get us what are the overall support reactions are. So coming to my total thing here, I could say, well, I need an area at the beginning of this. We'll call it area 1 in here. Area 1 goes from A, past B, all the way out to C. And then I need an area 2 at the far edge of this. Area 2. So 2 areas from my free body diagram, or the given picture in here. Area 1, they're both rectangles. Area 1 has a base of 15 plus 25. That'd be 40. So 40 times my height is 10, or this is 400 kips. Area 2, also a rectangle, has a base of 10 and a height of 10. 10 times 10 is 100 kips. From there, I can make my shear diagram. So we're going to start at 0, put a dot at 0, and immediately I have to resolve AY. I have AY, MA, and a distributed load all here. The distributed load will apply after everything else. MA doesn't do anything to our shear diagram, so it's really just AY. We go up by AY, we'll jump up immediately to 225. 225. From there, we can go all the way to the end of our interval. That internal pin isn't going to show up and do anything in our shear diagram for us. We'll talk through some useful info we could get from that, but we don't have to. But if I come in here, I can say my shear at the end of entirely area 1, all the way out to that roller. The next external thing that's changing in here is going to be my shear at the beginning, 225, minus area 1, or minus 400. Which would get me down here, 225 minus 400. We'll get a point here that is negative 145. Which would be my next piece. This is 255 for AY, not 225. 255. Let's update that really quick. Make my numbers make a little bit more sense there. 255. I just wrote down the wrong number. But 255 minus 400 does get us negative 145. Let's move that off the dash line. Negative 145. So just a linear decrease all the way down here to negative 145. At that point, I hit CY. That's going to push us back up. CY is 245. That should get us up to 100. So 100. And then I can say, well, 100 minus area 2. Area 2 is 100, gets us to the endpoint 0. Where we get this shear diagram working out for everything. And that's our first answer in here. Some important points on that. We have a 0 shear point right here. I am going to need to figure out what's going on there. We'll break that up and call it an x1 distance and an x2 distance in here. x1 and x2. x1, x2 as I come through there. One other important point though, right here at that pin, if I found what is my internal shear right here, if I found I could do it using proportional triangles, that value is going to end up being my internal connection, my BY, 105 right here. Really, internally, I could say I have a beam from A to B that should close out and be in equilibrium. If I went up 255 over, here I'd have BY pushing us down on AB, we close out. My next beam in there from B to C in the end would start at 0 and immediately go up to 105 and finish this entire thing. We've just taken those two shear diagrams and smushed them together to make one overall frame compound beam shear moment or shear diagram so far. But that would always be true for us. Technically, right here at this point, I have a force that goes down 105 and immediately one that comes back up 105. In that infinitely small distance, it cancels out and gets us no change in everything. But always right here, wherever that point is, our shear should be the value of our pin's y component. If we go to the moment diagram, I'm going to need to get a handful of areas in here. So I'll need to get in, what's my area of a big triangle on this? So we'll call that, I use area 1 and 2. Let's call that area 3. Area 3. Area 3, which is going to be a triangle for us, not the trapezoid here. We also have an area 4, and I can get in a fifth area, area 5. All triangles, so all 1/2 base times height. To get that, though, I'm going to need to figure out what is x1 and x2. So my x1, I'm using proportional triangles. x1, I can actually, let's do this as x1. I could work with that. It'll be way easier if I just make a big triangle here that goes all the way to the left edge. And that'll be my x1. So x1 over 255 equals x2 over 145. I could do a distance right here. It would be like an x3 over 105. It would still be proportional. We could work with that. But this is all going to be equal to my total x distance from A to C. 15 plus 25 is 40. Divided by that total change in height. 255 plus 145 is 400. Our area that we worked with, area 1. But I can solve that. x1 is going to get me to 25.5 feet. And x2 is going to get me to 14.5 feet. Working with those, I can figure out areas, my last 3 areas, and kind of get towards wrapping this up. So area 3 should be 1/2. Base is x1, 25.5, times my height, 255. Or that one's going to get us to 3251.25 kip feet. Area 4 is another triangle. Area 4 should get us 1/2. Our base is x2. x2 is 14.5. So 14.5 times our height, negative 145. Or this is going to get us to negative 1051.25 kip feet. And our very last area, area 5, is going to get us one more triangle, 1/2. Our base is just our entire distance here, 10, times our height, 100. Or this is going to get us 500 kip feet equals 500 kip feet. And that's enough. I can come in and start making my shear or my moment diagram. I'm going to work with the areas above it in any couple moments. So I have an MA. It's going counterclockwise. Remember, our rule tells us a counterclockwise couple moment does nothing to the shear diagram. We already saw that. But makes our moment immediately go down. So we're going to start at 0 and immediately drop down. So starting here at 0, we'll immediately drop down to MA, which should get us down to negative 2,700. Negative 2,700. And as we go on, we can add in area 3 to that. Our moment at the end of this, all the way out here at this point, actually we need to get to this point, at the end of area 3, should be the moment to start, negative 2,700, plus area 3, negative 2,700 plus 3251.25 is going to get us to increase in a parabolic shape in here until we get up to, where are we going in here? 51, right here, just barely above our x-axis. We're going to get to 551.25. Then we can go to area 4. At the end of area 4, our moment should be the moment at the beginning, 551.25, minus area 4, or plus area 4, but it's negative. So minus 1051.25. We're going to curve back down, and I'm exaggerating this parabola just to get space in here. But that's going to end us up at negative 500. Finally, in that last section, we would go that our moment at the end of area 5 is negative 500, the moment at the beginning, plus area 5. Negative 500 plus 500 would get us back to 0. Everywhere in here, our shear was sloping down, so I should be parabolic down at every single point along the way. And we could shade that in as well. Not above the line. But the one other key thing we can mention in here, right at that internal pin, right where our shear was 105, we are getting right here no internal moment. This is a 0 moment point. Again, we could close out a moment diagram right here. We would have a self-contained beam from A to B, a self-contained one from B to C, starting and ending at 0. We're just combining the two of them together because it's a compound beam. We're pinning two beams that are both in equilibrium to each other and making one overall shear moment diagram for that. Anytime there's an internal pin, our moment should be 0 because pins don't resist moment. It's also called a moment release in everything because it gets rid of all of our moment at that point. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you an A with JJ.